నమస్కారం. డాక్టర్ బిఆర్ అంబేద్కర్ సార్వత్రిక విశ్వవిద్యాలయం విద్యార్థిని విద్యార్థులకు స్వాగతం. ఈరోజు కార్యక్రమంలో
Hello viewers, welcome. In today's lesson, I want to present a theorem from functional analysis called Hahn Banach Theorem. This theorem states as follows: let capital M be a subspace of a real non-linear space capital N, and let capital F be a linear functional on capital M. Then this theorem says that this F can be extended linearly to a functional on capital N preserving the norm. Then F can be extended to a linear functional on capital N preserving the norm. Right. So here M is a subspace of a real normal linear space capital N, and F is a linear functional on this smaller space capital M. And what this theorem says is that this F can be extended to the whole space capital N preserving its norm. First, let us prove this theorem. Proof: we define capital B to be the set of all linear extensions of capital F to spaces containing this space capital M. So capital B is the set of all extensions of capital F to spaces or to subspaces of N containing capital M, and these are linear extensions, and these are preserving the norm, containing capital M, preserving the norm linearly to all linear extensions. That is what I mean by extensions. So capital B is the set of all linear extensions of capital F onto subspaces of capital N, that those spaces have to contain this smaller space capital M, and those extensions should be preserving the norm. And to show that this set capital B is non-empty, we have a lemma called Hahn Banach lemma that guarantees that this collection B is non-empty. For example, if we take what this lemma says is the following: if we take an element x naught from the complement of capital M, that is x naught belongs to n minus capital M, then if we consider the linear space generated by capital M and x naught, and then one can show that this linear functional F over M can be extended to a linear functional on capital M plus x naught, that is the space generated by capital M and x naught preserving the norm. This is what this lemma says. So using that lemma we will obtain that this collection B is non-empty. And now on this collection B we define a partial ordering. Let us define it as less than or equal to. We take any two members G1 G2 from this collection B. We define G1 is less than or equal to G2 if and only if domain of G1 is contained in domain of G2, if and only if domain of G1 is contained in domain of G2, and on the common domain, that is on the smaller one, G1 of x is equal to G2 of x, and G1 of x is equal to G2 of x on domain of G1, right. That is how we define the partial ordering, define the ordering on the set capital B. In fact, one can show that this ordering becomes a partial ordering on the set capital B. This is a partial ordering on on capital B. For an order to be a partial order, it has to satisfy three conditions. First of all, this has to be reflexive. From this definition, we can see that this less than or equal to is a reflexive ordering, because G1 is less than or equal to G2, because domain of G1 is in fact equal to domain of G1 and G1 of x equal to G1 of x for x belonging to domain of G1. Therefore, you have G1 less than or equal to G1. Similarly, if G1 is less than or equal to G2 and G2 is less than or equal to G1, one can obtain that G1 is equal to G2. This is antisymmetry, because if in case G1 is less than or equal to G2, we have domain of G1 is a subset of domain of G2 and G1 x equal to G2 x on this smaller set. If in case G2 is less than or equal to G1, we obtain this domain of G2 is a subset of domain of G1 and G2x is equal to G1x on domain of G2. So, if we combine these two, we obtain that domain of G1 is equal to domain of G2 and that G1x equal to G2x on the domain of G1. Therefore, antisymmetry also can be verified. And regarding transitivity, if we assume G1 is less than or equal to G2 and G2 is less than or equal to G3, we obtain that domain of G1 is a subset of domain of G2 is in turn a subset of domain of G3. Therefore, domain of G1 becomes a subset of domain of G3 and G1x equal to G2x on domain of G1 and G2x gets equal to G3x on domain of G2. Therefore, we obtain that G1x equal to G3x on domain of G1. So, that gives that G1 is less than or equal to G3, that is the transitivity. So, if we combine these three, we can show that this less than or equal to is a partial ordering. Therefore, B is a partially ordered set. Now, in this set B, let us take a chain C. So, C is a chain in the partially ordered set B. Now, using this set C, we define a domain, and on that domain we define a function. First of all, let us define this set. Let us define the set M0. M0 is union of this is union of domains of G's for G belonging to C. So, I am taking a chain C in the partially ordered set B, and I am taking those functions G that come out of this C. I am collecting all those G's and I am collecting the domains. I am taking the union of those domains and I am defining it to be the set capital M0. Now, on this set M0, we define the function capital G. So, capital G is defined as follows: G of x is equal to capital G of x is equal to small g of x for x belonging to domain of G, where G comes from the chain C. So, from the chain C, we collect an arbitrary element G, and for x belonging to this the domain of G, we define capital G of x to be small g of x. One can see that this set on the set capital M0, the function capital G of x is well defined. Capital C is a chain. Therefore, one can verify that this function capital G is well defined on the set capital M0. Now, in fact, by the definition of the function capital G of x, one can see that capital G of x becomes an upper bound for the chain C. Therefore, one can see that this G of x is an upper bound for C with respect to the partial ordering here, with respect to the partial ordering less than or equal to. By the definition of capital M0 and capital G, we can verify that G of x becomes an upper bound for the chain C. Now, we started with an arbitrary chain C. On that chain, we obtained an upper bound capital G. So, by John's lemma, the collection that out of which this C comes from will be having a maximal element, that is B, the collection B by John's right, B has a maximal element, B has a maximal element with respect to the ordering less than or equal to by the John's lemma. What this John's lemma says is the following: if in a partially ordered set, if every chain has got an upper bound, then that partial ordered set will be having a maximal element. So, our collection, the capital B, in that we started with a chain. For that chain we could obtain an upper bound capital G. Therefore, by John's lemma, this set capital B has got a maximal element. So, we have seen that the set capital B has a maximal element with respect to the ordering less than or equal to, say it is F naught. Now, let us call the domain of F naught to be the set M naught. Now, let us claim that this M naught is equal to the whole space capital N. Let us start with negation to prove this claim. Let us say this M naught is properly contained in capital N. Then we can take an x naught coming from N minus M naught. Then if we look at the space generated by M naught and x naught, on this space we can define a linear functional f naught dash as follows. F naught dash of x is f naught dash of m plus alpha x naught. This is defined as f naught of m plus alpha times r naught, where r naught is suitably chosen. Now, x is belonging to the space generated by m naught and x naught. So, it is of the form an element small m coming from the space m naught plus a scalar multiple of x naught. Now, we are defining it to be f naught of m plus alpha times r naught, and we choose r naught properly. So, if we define like this, one can see that this f naught dash becomes a linear functional. In fact, we can choose r naught in such a way that the f naught dash and f naught both have the same norm, and this way we can obtain a linear extension of the function of the maximal element f naught to a space m naught plus x naught, which is the space generated by m naught and x naught, which in fact is a space larger than the space m naught. So, this way we get an element which is larger than and different than the maximal element f naught, and this contradicts the concept of the maximality of f naught. Therefore, this is not possible that m naught is a proper subset of n. Therefore, m naught has to be equal to n. Means we could obtain that the linear function f could be extended to the whole space capital N. So, by Hahn Banach theorem, if in case M is a subspace of a real normal linear space capital N and f is a linear functional on capital M, then this f can be extended linearly to capital N and preserving the norm. Means the f will have the same norm as its extension, say G, to the whole space capital N. So, here what we have discussed is the Hahn Banach theorem for real normal linear space. In fact, the same theorem can be shown to be holding good for even complex normal linear spaces also. So, one can verify that if you replace this real term by complex, then also one can see that this theorem holds good. The Hahn Banach theorem holds good for complex normal linear spaces also. It is because when in the statement of the Hahn Banach theorem, if we replace the normal linear space N by complex normal linear space capital N, then one can show that that if you take M is a subspace of capital N, and on M we have a linear functional f on M, then this f can be extended to capital N, preserving its norm. It is because we have the following: if in case f is a complex linear functional, on capital M, then we have f of x is equal to something like g of x plus I times h of x. We are saying f of x is a complex linear functional. Therefore, we have f of I of x is equal to I times f of x, and if we compute f of I of x and if we multiply this by I, then we can show that f of x becomes f of I of x is g of I of x, then plus I times h of I of x, then this I into f of x becomes I into f of x is I into g of x minus h of x. So this h of x gets equal to minus g of I of x. Therefore, f of x will be equal to g of x plus I times h of x, that is minus I times g of I of x. Now one can show that this g of x, which is a real linear functional, can be extended to the whole space capital N. Similarly, this h of x also can be extended, and one can show that the norm of this can be preserved and these can be linearly extended to the whole space capital N. Thereby one can show that this f can be extended to the whole space capital N, preserving its norm linearly. So that is how one can do the complex case of the Hahn Banach theorem. Now let us look at a few consequences of this Hahn Banach theorem. The first one is the following. So consequences of Hahn Banach theorem. Number 1, let us say we have a normal linear space capital N and x naught is a member of capital N and is a non-zero element. Then one can find a linear functional f on N such that f of x naught is equal to norm of x naught and norm f is equal to 1. This is a consequence of the Hahn Banach theorem. We prove it as follows. We may consider the linear space generated by the non-zero element x naught. So this is the set of all elements alpha x naught such that alpha belongs to the field. Now we define f of x naught to be f of alpha x naught to be alpha norm x naught. So if we define like this, we can see that this f becomes a linear functional on this linear space, and this this x naught is coming from N. So this is a linear subspace of capital N, and we can see that this is linear and its norm is 1. And we know that by Hahn Banach theorem, the linear functional on this space, which is the span of x naught, this linear functional f can be extended to a linear functional on capital N, preserving its norm. And we have, if we take alpha equal to 1, we have f of x naught equal to norm x naught. So that is how one can apply the Hahn Banach theorem to get a linear functional on a non-trivial normal linear space having norm 1, having its norm value equal to 1. Let us look at another consequence of Hahn Banach theorem. Let us call it number 2. Let us take capital N to be a normal linear space or the set of real numbers or complex numbers, and let M be a subspace of capital N. Let this be a closed subspace, let capital M be a closed subspace of capital N, and let x naught be coming from the complement of M. Then one can show that there exists a linear functional f such that f of m is equal to 0 for small m coming from capital M, and that f of x naught is not equal to 0. And to do this, we use the canonical map and proceed, and we use the Hahn Banach theorem, and we obtain a functional capital F on the whole space capital N satisfying this property. That is, we have the normal linear space capital N over the set of real numbers or complex numbers, and M is a closed subspace of the whole space capital N, and x naught is coming from the complement of capital M. Then we can find a linear functional on this whole space capital N f such that f of m is 0 on the set capital M and f of x naught is non-zero. to do this we use the canonical map. Then we have another consequence of this Hahn Banach theorem. It is as follows. Let us call it number 3. Again we take n to be a normal linear space over the set of real numbers or complex numbers, and M is a subspace of capital N, and say x naught is coming from the space capital N. Then let us define D to be d of x naught comma m to be the distance between x naught and m, that is infimum of norm x naught minus m, such that it is norm x naught minus small m, such that m comes from capital M, right. So let us say this is positive. Then we have the following. Number 1, f of m is equal to 0. Number 2, f of x naught is equal to d, and number 3, norm f is equal to 1. So we have the following. N is a normal linear space and M is a subspace of N, and x naught is coming from capital N, and if in case the distance between x naught and M is positive, then using Hahn Banach theorem we can obtain that there exists a linear functional f on the whole space capital N, such that f of m equal to 0 and f of x naught is equal to d and its norm is equal to 1. In this lesson we proved Hahn Banach theorem for the real case, we discussed the complex case, and we assumed the Hahn Banach lemma which we proved in the theorem, and we discussed 3 consequences of this Hahn Banach theorem.